Okay, good afternoon. My screen is visible.
Yes, sir.
Yes, sir.
It's moving. Second slide, see that? Yeah,
Yes, sir. It is moving.
okay. We'll see that first unit we'll start today. General consideration of DC and AC transmission system. It is purely theoretical orientation. Only the comparison of AC and DC transmission with respect to different parameters, economic parameters, technical way, and then reliability wise. So that is one big question. Another one is the applications and then modern trends, advantages, disadvantages, all very basic things. Now, before starting this, there is a brief introduction about this unit. You can see the HVDC transmission is advantages over AC transmission in specific situations, because some of the cases AC also will be advantage, but in overall with respect to specific situations, DC is the more advantage, because with respect to distance and then with respect to power transmission, all this aspect DC is the more advantage. That is the reason nowadays all some cases existing transmission lines also they are converting to the DC fashion. The lot of advantages are there. Anyhow, all these things will cover in the comparison of AC and DC transmission with technical aspect. And then this link, HVDC link, was between Swedish mainland and then Iceland of Gotland in 1954. So this is the first link they established in 1954, and that is used in the mercury arc walls. We discussed yesterday some of the slides table in the which year and what is the voltage level and what is the distance, and then in which country they established, what type of wall they used. All these things I described in the table fashion. In that way, you can see here mercury arc walls. So this is used initially in that system. 20 megawatt underwater link they used up to 90 kilometers. So later on, this mercury arc walls are not used. They used as a thyristor walls. So this is the in first in 1954 they used as a mercury arc wall the 20 megawatt underwater link. There is a distance of 90 kilowatt. Since then, what will happen? The study increased in the application of HVDC transmission, and means the advantages of all the aspect of in terms of semiconductor device technology, all these things. Then the later what they had done is thyristor walls used in a converters. In a converter, as it is a rectifier station or in maybe in the inverter station, preferably what they will use in the olden days is a mercury arc wall before developing the semiconductor devices. Later on, lot of research takes place and they invented there is a thyristor wall and they used in a converter. All the converters, whether it is a rectifier station or inverter station, now they are using as a thyristor walls, and they become as a more attractive. Because of this there is a lot of future. This is in terms of capacity wise, voltage and current rating capacities all are very high enough. That is the reason they replaced the mercury arc wall to the thyristor walls. And the first in HVDC system in the thyristor wall, previous one is a mercury arc. Now in 1972 they used as a thyristor walls. That 320 megawatt back-to-back DC transmission between the power systems, Candian, Province, and the new Brunswick or Quebec. So some this area they used as a 320 megawatt back-to-back DC transmission, because there is a links are there in the different types of link, and based on the area and there may be availability of ROW, all these things they consider what type of link they want to use. Here is a back-to-back in the sense bidirectional power flow. The two conductors they can use positive and negative, but only one conductor also sufficient to transmit the power. And thyristor valves are now become as a standard equipment for a DC converter station. So now anyhow no other devices are replaced with this, because the thyristor valve is very powerful one, but only for low rating only we can use some other devices, but preferably all the things converter stations they will use as a thyristor valves. Recent development in conversion equipment has reduced their size and cost and reliability, because the device itself, then lot of SCR family devices they improved a lot, and you can see that some of the diagrams in Google, you may notice that different stages and different years they have their size of that and rating, but now very simple size and we can capable to withstand all the aspect of whether it is a reverse braking capability or forward breakover capability, and then peak surge voltages and repeated reverse voltages. So all these things can able to withstand the device because of the improvement that leads as a size also reduced now, and cost as well as reliability. Reliability aspect is very important aspect in this case. If the normal case, if any device fails, automatically the substation has to be, like suppose if transformer is there, if transformer fails, what we have to do? Either you have to replace it by standby unit you have to do. Meanwhile, it has to be stopped. But whereas here, reliability aspect, it is a number of years it can withstand. So they analyzed some of literature. I think I already mentioned in introduction classes. Huge years, even 12 years, 10 years, something like that. They consider that many number of years the failure is not there. So failure may occur after 10 or 20 years, so that you can reliability aspect is more and more. That is already there. I will show that table also with the existing literature. The development has resulted in a more widespread in a DC transmission. Because of these advantages, cost wise and size of that equipment and the reliability aspect, now they used HVDC transmission more and more. In North America, total capacity of HVDC link in 1987 was over 14,000 megawatts. So now we can able to observe that is the advantage. Even 1987 itself, in the America they used this much power transmission capability. But later on in India also, I shown you one of the slide. Many places they used even 800 kV transmission line also in India. So this is the impact in the HVDC transmission. And then industrial growth of a nation, that everybody knows this sentence, increased consumption of energy, particularly in electrical energy. So one person or country wise, what is the consumption of energy in India or any other particular country, that shows their capability, the growth of the country. So if the growth is more and more, automatically power consumption will be more. That is on, like in houses also. You consider below poverty line, and then middle class and the upper class something. If they see their consumption bill, that shows their capability or their richness or something. So that is what here they mentioned. Then the industry growth of nation, they will use the electrical energy, and this has led to increase in the generation and transmission facilities to meet the increasing demand. So because of that, industry growth is there, means we need to generate more and more power. And then USA, early 70s, this analysis is not present one. In early 70s, the demand is doubled every 10 years in USA. But same in India, every 7 years. That means, so we are increasing rapid way. I mean, how we are utilizing the power, means a industry may be industry growth is more, and then individual commercial consumption or domestic consumption. So in terms of all the aspect, the growth of consumption, they mention in that a 70s base parameter, demand is doubles in every 7 years in developing countries like USA and all. The demand is doubled in every 10 years. It requires considerable investment in the electric power sector. So that leads, we need to invest more and more. That's why you can see in our India reforms also. I think 2005 there is a Electricity Act is there. That is a lot of reforms are made in the world. Before that, prior to 2005, I think so. So we no other parties can generate a power. We need to buy only through electrical whatever government sector is there. But later on, everybody can able to generate their own power, and they can able to sell their power like that. Lot of reforms are made. That is the increasing sector in the electrical sector. That leads cost also going down and down. With my best of knowledge, I know that solar energy in 12 rupees per unit cost. That is what agreement also with central government, MHRD, I mean, new renewable source. In that area, we can see that our SECI, the central government sector, so they will tie up with 25 years agreement with the price of 12 rupees initially, around 2011, prior to 2011. Cost of solar generation is 12 rupees per unit. The government has to pay, and in addition to that, there is a carbon credits also will be there. Carbon credit in the sense, because of solar generation, what will happen, you are reducing the pollution. That's why each industry has to buy, either they have to generate the solar power or renewable power, or they have to buy their certificates like a carbon credit certificate from the solar plant owners. Then that price is nearly 8 rupees per certificate. So like that, the vendor will get lot of money those days. And later what will happen, the price is going down because of the technology improved in a solar panel technology and inverter technology, and more and more generating plants are installed. So all these aspect leads to the price of that solar power. Now it is reduced to 2 rupees. Even some bidding also they are giving 1 rupee 90 paise or 1 rupees 40 paise, something like that. So that much cheaper now. So these are all based on the development in the sector, power sector, or in the development in the what we call it as semiconductor devices, and then solar panel aspect, and then wind generation station. All this improvement will leads the cost of the power is reducing. That's what investment in the power sector is we need to consider more and more. Now we can see this environmental conditions also sometimes dictate the setting of power station at the remote location. So this is the major thing, environmental conditions. So like if we want to install as a thermal power plant, then lot of pollution will be there. So now the area, based on that, all the things will decide the setting up of the power plant in the remote location. So large hydro stations are invariably distances from the hundreds of kilometers from the load center, because this cannot be installed where you are is based on your wish. Because the hydro plant, we require a lot of considerations, the availability of water and all these things, and dam construction. So many factors are influenced to install a hydro station. That's why generally load stations may be far away from that generating stations, the huge distances. In that, if you transmit as AC, even olden days there is nearly 33% of power losses are there. But now they reduced a lot more because of again technology. The need to economize on costly investment in the generation, reserve sharing of benefits in utilizing the variability in generation mixed and load pattern have given rise to the incorporation of the neighboring system, development of a large power grid. So that what will happen, they will use to develop a large power grids, the interlink all the generating stations, and will reduce that way also we can able to minimize their cost, one aspect. And remote generation and system interconnections lead to the search for efficient power transmission at the increasing the power levels. So there is a normally in remote locations, if you use that installation of the plant, the transmission problem and that also leads. But now there is a microgrids are there, and that will minimize the lot more transmission losses in general, because wherever load center is there, there you can able to install as a microgrid and they can utilize their power there itself. The increase in voltage level is not always the feasible, but as you are aware that by increasing the voltage level and we are reducing the losses, all these aspects, but that cannot be feasible all the cases. The some certain voltage level only it can withstand, because again insulation problem, all these things, conductor size, all impact will be there on protection components, that is a switch gear, all these things. Now the problems of AC transmission, particularly long distance transmission, has led to the development of a DC transmission. So AC, if we want to transmit very long distances, that will lead as a major problem. To overcome all these problems, now the DC transmission is preferred. That's what I oftenly say in the introduction also. I will show that comparison graph also. And however, generation and utilization of power remains at AC currents. So whatever consumption is there, we are using as a AC transmission only. That's the reason one of the factor is here, cost of DC transmission is more for the lower distances. That is the one problem in DC transmission, because we need to convert that into DC as well as again convert back to the AC. For it, like we have to use the two-way conversion. That's the mention here, AC to DC in the sending end side and back to AC at the receiving end side. That is the reason two substations are very important. That is, one is a rectifier station, another one is a inverter station. Inverter station will be installed in the receiving end side, and rectifier station installed in the sending end side. And the converters are static, because these are no rotating parts, using high power thyristors, because that converters consisting of whether it is a 6 pulse or a 12 pulse, high power rating devices only used in the same can be switched from rectifier to inverter or inverter to the rectifier. Power reverser also possible. That is anyhow known to you and come back in the second unit also. There is a two stations are as look as same. Only the thing is based on your control strategy, whether we want to use it in the what you call it as a rectifier station or a inverter station. We need to operate that device based on our firing angle. Suppose I want to transmit power from sending end to the receiving end. First station act as a rectifier station, second one will act as a inverter station, or vice versa. Second receiving end side will make it as a rectifier and sending end will be as a inverter side. So that way bidirectional power reversal is possible. The HVDC transmission made modest being in 1954 when 100 kV and 220 megawatt DC link was established in the first one, that is already mentioned in the first slide. Until 70, converter station utilized mercury arc valve, and later it is converted to as a thyristor valves. So the large device is not in the range of 5 kV and 3000 ampere or 3 kV. Highest transmission voltage reached in plus or minus 600 kV, but now it is available even plus or minus 800 kV line also is there. That is the brief introduction about first unit. Now we'll come to the question is comparison of AC and DC transmission system. So there is a three major comparisons we need to come across. So one is economic wise, another one is a technical wise, and third one is a reliability. So these are the three major. This is very important question. If this is essay question, you must explain all the three factors, that is economic and technical and reliability aspect. The merits of the two modes for transmission AC and DC, which need to considerable by a system planner based on the following factors. So these are the three main parameters we need to compare, and you can conclude which one is a preferable one. Economics of transmissions and technical performance and reliability aspect. Major feature of power system in the continuous expansion necessity by the increasing power demand, because power demand is very I mentioned in the old logic I mentioned as every 7 years and something like that. So we have to invest more and more in the power sector. This implies that establishment of particular line must be considered as a part of an overall long-term system planning. So we need to consider as a long-term system planning. There is a modern trends in HVDC transmission also, one of the factor. We will see that also. And first we will see the economics of power transmission. What is the meaning of economics is in terms of the cost wise. That's all, nothing more than that. The cost of transmission line, or if I say cost of generation, like a cost of transmission line, that is there in a power system also. Optimal, I think power PSOC subject or somewhere you will get it, optimal power flow control. So what we will do there is, there is a generating station is there. We may have many number of generating units, 4 generators or 3 generators or something like that. Now I want to find what is the optimal cost, or you can say the optimal power flow, means that how to minimize the cost of a generation. There what you will do, all the 3 generating stations may not be in the same place, they may be in the different places also. Then when you want to generate a power, there is a effect based on the coal, the distance from coal mines to the what you call it as a generating plant, and in that area employee salaries, so the land cost, so many parameters are incorporated. There is a formula for you for the cost of generation. AIPGA square plus BIPGA plus CI. ABC are the coefficients of the particular generator, and then PG, the generator 1, generator 2 and so on. All these generators, how much it is generating, and we are calculating as a cost of a generation. That is the actual thing. But now what is the optimal cost of generation means, instead of generating more power from the faraway distances of coal mines and all, what they will minimize the generation there, and they can able to generate the more power in the which generator is generating as a less cost, because the A, PA, PG, CA coefficients are less. Then that way there is algorithms are there, conventional algorithm and heuristic algorithm. Using that algorithm, they will find which generator, how much it is going to generate to get it as a minimum cost. So that is the aspect, and we will find the generators generations, and appropriately you are operating as a plant that will give as a minimum cost of a generation. Similarly, minimum emission, and another one is a minimum voltage deviation, like that for all other instant or minimum losses. So based on your objective, we can able to find the generations, and then because we are diverting that power flow, you can able to get it as a minimum loss also, because the some of the transmission lines may have more resistance. Let us assume that if you are transmitting power through the transmission line, you will get more loss. Then what you will do, they will divert power to some other line, and so that you can transmit more power through that line, you will get as a less losses. How to increase the power capability, transmitting capability? That's what fax devices and all they used, and they reduce the impedance offered by that line using the series compensators and all, and they will allow maximum extent of the power through the transmission line. Instead of erecting as a new line, what they will do is using the controller, they will able to transmit more power. So you do using these all scenario, you can able to get it as a minimum cost wise or minimum loss wise and voltage fluctuation wise, stability wise. So many parameters that will lead to the optimal power flow control will decide that. Similarly, in case of cost of a transmission line, now what you will do here, only the transmission side, not a generation side. Cost of a transmission line includes the investment and operational cost. These are the two parameters we need to consider to decide the cost of a transmission line: investment and operational cost. What are the investment parameters in a transmission line? uh, because land is required. That's what right of way, ROW. So that is a land. And transmission towers, because these are all fixed cost, more or less. So transmission towers we need to install, and conductors are required. RYB and neutral, all these things. Insulators are required. Terminal equipments, like that. Many parameters we need to consider for the investment. And another one is a operational cost, include the cost of the losses, because when the power is transmitted through transmission line, some of the loss is going to be takes place. That we call it as a operational cost. So that is nothing but a cost of a loss. So all these two things, one is the investment and operational cost, that will decide as a economics. So characteristics of insulators vary with the type of voltage applied, because the insulators may not be the fixed one, depends on your voltage levels. All these things will varies. And for simplicity, if they assumed that the insulator characteristics are similar for both and AC DC, depends on peak level of voltage applied with respect to the ground. Now then can show that lines designed with the same insulator level, we can see that, let for example we consider as AC and DC transmission characteristics of the insulators are same, even though when you are designing as a line, in the DC line can carry the much power with two conductors, only plus and minus with respect to the ground, as an AC line with three conductors of the same size. Now this is the scenario, that means same power we need to carry only the two conductors here, and there will carry the three conductors. In that is, we can see that one simple analysis I made it here. AC power formula is 3 Vp I into cos phi, let it be root 2 is in the RMS concept. So just 3 V I cos phi, and DC side two conductors, 2 into V into I, let it be. That Vp is a peak voltage with respect to the ground, and I is a effective current rating of the conductor. Then, so if I carry the current, or let it be as a power, in the AC side, this is the formula, and DC side, this is the formula. Let the same power I want to transmit, PAC is equal to approximately equal to the PDC. This implies that for a given power level, what is the observation? DC line requires less right of way, because here three conductors are required and towers, many things is essential there. Whereas in AC side, same amount of the power, we required only less right of way. Simpler and cheaper towers. You can see that no complication is there to construction of the towers. It is only the two conductors or even one conductor, let's consider. So therefore it is very simple and cheaper towers, and reduce the conductor and insulators cost. So what will happen? Conductor size is reducing and then insulators cost also is reducing, because if I use the AC side, we need three conductors. Each conductor we have to use as insulator. So all these aspects, it shows what, when you are transmitting the same amount of power through DC, this is the benefits. Conductor size will reduce, insulator cost will be reduced, right of way will be reduced. So all these things are benefited. And power loss also reduce. Obviously, when conductors are less, power loss also will be less. Only two conductors, so that's the reason you can see that 65% of that AC with the same current carrying capacity of the conductor. So that much benefit will be there. The absence of skin effect, because in DC skin effect will be absent, also benefited in reducing the power losses marginally, whereas in the AC case, due to skin effect, some losses will be there. And what I am doing is I am comparing AC and DC in terms of all the three major subheadings. One is economics, and then technical and reliabilities. Now we are come across the economics here, so that means if power losses are marginally reduces, the cost also obviously will reduce. So because if you are wasting the power, that will come under a cost of generation also. The dielectric loss in case of power cables is also very less in the DC transmission losses. And then the corona effect tends to be less significant in the DC conductors than AC, and also lead to the choice of economic size of conductor with the DC transmission. See, all these factors will influence on the DC transmission. Here the area wise, then towers and conductors, insulators, and then skin effect, dielectric classes. Then another one is a corona effect. So all these parameters is a benefit in a DC side. The other factors that influence the line costs are the cost of compensation and terminal equipment. Now, one more thing, cost of compensation. Here, in case of AC, compensation also required, whereas in case of DC, compensation is not required. So that also will influence on that. DC lines do not require compensation. No reactive power compensation based on the line loading. You can see that whether it is a nominal load or over or lesser, based on that it has to absorb the reactive power and it has to generate the reactive power, and to neutralize that we need to compensate reactive power compensation using the fax devices, all these things. Whereas in the DC line do not require compensation, only it will be occurred in a AC line. So terminal equipment costs are increased due to the presence of converters and filters. Only one problem is terminal equipments here, that cost, that's what initial cost, or you can say that there is a increase due to the presence of converters and then filter. I already mentioned in the introduction classes, I quoted very specifically in a converter station, whether it is a rectifier or inverter, we need to use a AC filter as well as the DC filters. So that is one factor. Another one is a two stations or installation cost of the two stations are more. That is what I mentioned here. Presence of converters and filters, the cost will be increases. So now this is the break even distance. We can notice here what you call it as in the AC as well as DC. Suppose the AC line, you can see cost versus distance. X-axis is a distance and then Y-axis is a cost. In this aspect, starting point you can notice this one and this one. So what is this? Distance 0. So that means installation cost or a starting cost, or you can say that. So when you compare to DC, starting cost or installation cost of a AC transmission line is less comparatively DC transmission line. So in DC transmission line, you can see here the initial cost is very high when comparatively AC. And then you can see some distance, you're increasing the distance, the curves will vary like this. When if we are increasing distance, what is observation in a AC side? If distance is increasing gradually, cost of a transmission line also is going to increase proportionately. So you can see that it is gradually varying, nowhere it is decreasing or nowhere it is stable. If we are increasing the distance from starting point onwards, let after installation cost, it is gradually varying, continuously varying. But whereas in the DC side, if you are increasing the distance, slightly varies and then it will vary further. But some point of intersection, AC and DC point, here you can see that below this intersecting point, DC transmission is a costly than AC transmission. But after interconnection, means break even distance, what is the observation? AC transmission cost is high than DC transmission cost. That shows that whatever installation cost is there, by increasing the distance, that will add up with this, then gradually the cost is going to be minimized, because many loss parameter, many aspect is absent in case of DC, like what we discussed, the corona, skin effect and tower requirement and area. So all these aspect also included, whereas in the AC side, if the distance is varies or increasing further, all other losses also will come into the picture. Towers, we need more towers, area we need ROW also more, and then losses are more, skin effect is there, corona is there. So once that will be proportionate with the distance. But whereas here, due to that absency, you are getting lesser cost of a transmission, but it will happen only after break even distance. So now what is the break even distance here? So nearly 500 after 500 kilometers, or let it be 500 to 800 kilometers, then you will get it as a, what you call it as, DC transmission is a preferable one when compared to the AC transmission. So that's what break even distance. After break even distance, DC is preferred, and below that AC is a preferable one, that you can mention. And then that's what I mentioned here, cost of transmission with distance of AC and DC transmission. AC tends to be more economical than DC for distance less than break even distance. That is what the intersecting point shows from the plot. So only the longer distances AC will be costly, but after break even distance can vary from 500 to 800 kilometers in overhead lines, depending on the per unit line cost. That will give as a less cost. Based on this diagram itself, we can say that after break even distance, cost of a DC transmission line will be less comparatively AC. And then we'll move on to next one is a technical performance. In a technical performance, there is a lot more parameters are there. We have to see all stability, line compensation, then voltage limit, current limit. So like that in use of AC transmission problem. So many things we need to discuss. They will see one by one. In a DC transmission are more positive features within a lagging in a AC transmission. Because when you compare to the DC, lot of positive features are there in a DC transmission when compared to the AC. Mainly due to the fast controllability of a power DC lines through converter control. This is what when you observed, AC side, let it be P is equal to V1 V2 by X into sine delta. Whereas here in case of DC transmission, control is very fast rate. Only thing is, I already mentioned, no, at what instant you want to fire, you can fire the devices through firing circuit. That means, laser circuit or light triggering. So with that, you can easily break the junction J2 and it is going to be conduct. Series operation of devices conduction also possible. So many features are there. That is the reason you can say that fast controllability of a power in DC lines through converter control. There is a some advantages I mentioned here. Full control over the, I'm comparing with AC only. Full control over the power transmitted. You can easily control by changing the firing angle. The ability to enhance transient and dynamic stability in associated AC networks. Fast control to limit fault currents in DC lines. This make it feasible to avoid DC breakers in a two-terminal DC link. So fast control to limit fault current in a DC line. Then automatically DC circuit breakers, two-terminal circuit breaker, when you compare to, I already mentioned in the introduction also, comparatively AC circuit breaker, DC circuit breakers are cheaper. So that cost also is going to be minimized. And then in addition to DC transmission, overcomes some of the problems of AC transmission. They are described. One is a stability limits. Stability limits means there is a power transfer in AC line is depends on angle difference between the voltage phasor at the two ends. That's what Vs VR by X into sine delta. That is the angle is going to control. So that angle is a difference between the sending end voltage and receiving end voltage. Power transfer level in this angle increases with the distance. So based on the distance, that also I will show the graph. Maximum power transfer is limited by the considerations of steady state and transient stability. Power carrying capability of AC line is inversely proportional to the transmission distance, whereas power carrying ability of a DC line is unaffected in the distance. This is the major point. Using the graph also, this sentence has to be. The based on the distance, the power is inversely proportionate in case of AC, but in case of DC, that will not affect the DC side. This is the curve, power transfer capability versus distance in terms of the AC as well as the in terms of the DC. So in terms of DC, you can see that capability, power carrying capability is not with respect to the distance, but whereas in respect to the AC side, increasing the distance capability, the transmission, the conductor, or you can say that the line capability is going to be dropped down. So this is the major problem in that area. That's why in the stability limit also will be more in case of the what you call it as DC. And voltage limits, you can see that normal working voltage and the over voltage caused by switching surges and lightning must be limited to value that will not cause puncture or a flashover of the insulator. So therefore, we need to take care of the voltage levels to avoid the flashover in the conductors, or I mean insulators. AC line voltage control is complex by line charging and inductive voltage drops, because in the line On the long distance line there is a capacitance and then inductance, all these things are there. On HV overhead line, switching surges have become as more serious transient over voltages. On AC lines, attempts are made to limit them to peak value of 2 to 3 times of normal crest voltage. Can able to limit, because the crest voltages with lesser time very high voltage will be obtained, that has to be limit only 2 to 3 times of the normal crest voltage. But whereas in the DC side, the lower than that of only 1.7 times of normal voltage only it will happen. And then was due to the corona maximum working voltage or the minimum conductor size is limited on a overhead lines. So that is also the limitation in AC transmission line. But in cables, normal working voltage is usually to the limiting factor. Cables and all, we cannot transmit more and more power when compared to the overhead lines, and distance also limited in the cable, cannot be transmitted very long distances like 40 kilometers, 50 kilometers, something like that. In case normal working voltage is very limited factor, insulation will be withstand a DC voltage higher than the crest of the alternating voltage. So it can withstand the more voltage. And current limit also you can see here, temperature of a conductor must be limited in order to avoid damage to the conductor. So this is also the major issue. If your temperature is not limited, automatically the conductor sag will increase, and cable of insulation, all these things it has to withstand. Hence current in the conductor must be limited in accordance with the duration and ambient temperature. If temperature rises also, that effect will be there. And this also same as a current limit, not a voltage control. On long distance AC overhead lines and short distance AC cables. So preferably, I just mentioned, no, for long distances overhead will preferred. For short distances cables we can use. The generation and absorption of reactive power by the line itself is a serious problem. So generation as well as the absorption of because that's what I mentioned somewhere in yeah, in line loading I mentioned there. That's what the compensation, or you can say the reactive power control is a major issue. The line produced reactive power, you can see that reactive power V into IC, that is equal to V into IC is nothing but V by XC, then we'll get it as a omega C V square. Similarly, line consumes the reactive power. First one is a produced the reactive power, next one is a consumed the reactive power is I square omega L. Then let consider what is L, what is C is a shunt capacitance and series inductance per unit length. Reactive power produced by the line is equal to the consumption. Let consider QC is equal to QL. Then what will happen? V by I, that is equal to root of L by C. That is nothing but a Zn. That is a impedance. In this case, the load impedance as a Zn known as a surge impedance, that is about 400, and then bundle conductors and about 300 and cables. Normal thing is 400 and bundle conductors are 300 and cables are 40 ohms. So this is the surge impedance. Now we can, how the control is taking place, we have to maintain voltage is constant, that you can see that power carrying by the line so as to Pn is V into I, that is equal to V square by Zn is called a surge impedance loading. It depends only on the voltage and impedance of the distance. You can see that surge impedance loading depends on the voltage and impedance. Now this diagram will give the clear picture. On line carrying is a natural load, that is a Pn. The magnitude of voltage is same throughout the sending end to the receiving end in the curve 1. Let it be as a what I call it as dotted line. You can see this. this dotted line, whether it is a sending end side or in a receiving end side, the voltage magnitudes are same. Now, load demand is not constant. Always it varies vary with the time because it is not a fixed one. In overhead line, most economical load is greater than the natural load. So now we can see the curve 3, this one, P is greater than Pn, then what will happen? That in this case, net reactive power is consumed by the line and must be supplied from either of the end. So now net power, that is the reactive power, is consumed. It is consumed from the line. So there you have to compensate. So must be in the either side, because you can see that voltage is dropped down. If you not compensate, that will be continuously dropping down. Similarly, other one you can see, if Pn is maintain in the both end, equal amount of reactive power supplies in the both end. So now if the load on the line is lesser, that means P is less than Pn, net reactive power is produced by the line and is delivered to one or both sides. So that's the again same problem is arise. You can see that if P is less than Pn, then what will happen? It will generate the reactive power. So voltage will be rises. So it will produce. That means it is generate. So with equal voltage at both ends you have to maintain. Then you have to consider again compensation is required. So these are the some of the technical features. So we'll see the other features in the next class. If you have any doubt, you can ask me. Otherwise, you post the attendance and then leave. 27 are present.